Okay, so in the previous class, we had seen how the AC currents basically passing through transmission lines can reflect of load impedances if the load and the characteristic impedance of the circuit are not matched, right? So in today's class, we'll be talking about the same thing, and moreover, we'll be solving a few problems regarding this topic, as well as there will also be a few problems regarding the Smith chart. Now, are you guys all familiar with the Smith chart? Have you guys been taught about Smith charts and things? Yes, yes. So Smith chart is basically drawn on a complex plane where the reflection coefficient is a complex quantity. So basically it is consists of a set of circles drawn on that plane. And using the Smith chart, you can actually plot lines of like constant resistance or constant reactance and things like that. So nowadays these quantities can also be computed computationally with the help of computers. But previously, before computers, people used to use these Smith charts to calculate these quantities. So that is an easy way of doing it. But since I don't have a Smith chart with me, so I won't be covering the problems on Smith chart. Instead, I'll be covering the other numerical problems which have been given in this assignment. So let me open the assignment then. So is my screen visible to you? Okay, all right. So, for example, this first question over here, it is based on a Smith chart only. So, for a normalized resistance R equal to 5, what is the center of the R circle? So, can uh, can anybody tell me which one will be the correct answer for this? So, the correct answer for this is 5 by 6 comma 0. Why? Because the normalized resistance is given as 5. So, the center of the R circle is given by this formula R by R plus 1 comma 0, which is equal to 5 by 6 comma 0. Okay, so R circle is basically a circle of constant radius R equal to 5, and the center of this circle lies at 5 by 6 comma 0 on the Argand diagram. Okay, any queries about this one? Okay, if there are no doubts or queries, then the next question is also similar. So this talks about a normalized reactance instead of the radians equal to plus minus 5. The radius of the X circle is what? So over here the radius of the X circle is basically 1 by reactance, which is equal to 1 by 5, that is equal to 0.2. So this is of the radians of the circle with constant reactance. And question 3 over here, it is telling us choose the correct statements from the following. So which ones are the correct statements out of these four sentences? So do you know of a quarter wave transformer? Yes, yes. So okay, 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 I see. Okay, okay. So these are a few characteristics of the quarter wave transformer. So the first characteristic is this first sentence, that the quarter wave transformer is a narrowband device. So it works on a narrow range of frequencies and does not work on a broad range. So it's a narrowband device. And the second characteristic is that the quarter wave transformer is frequency sensitive device. So for frequencies outside this narrowband, this quarter wave transformer won't work. So these two sentences are correct sentences, 1 and 2. The third sentence is incorrect, that it is not a wideband and it is also not frequency insensitive. Okay, so the third sentence is false. And regarding a single stub turner, this fourth statement is also correct, that the single stub turner consists of an open or short-circuit section of transmission line of length t, which is connected in parallel with the main line at some distance. So this is another characteristic of the single stub turner. Okay, so the correct statements among these four are 1, 2 and 4. Okay. So then moving on to question 4. In question 4, we have a 50 ohm transmission line of length 100 meter, which is terminated by a 200 ohm load. Now, if the step voltage of a magnitude 12 volt is sent out by the generator connected to the line, then the transition time is what? So, we have to find the transmission time of the voltage in second. So, you have the source sending out a set step voltage of magnitude 12 volt, and we have the speed at which the the speed of transmission of the electromagnetic wave through this line is 10 power 8 meters per second, and Zg is the generator voltage, and 50 ohm is the characteristic impedance of the transmission line whose length is 100 meters. So given these quantities, transit time is actually a very simple thing. So for transit time, you have to basically divide the length of the length of the transmission line by the velocity of the propagating electromagnetic wave. So here the length is 100 and u is given as 10 power 8. So as you will see, the transit time is basically L by u, which is 100 by 8, that is 1 microsecond. Okay. So this part about transit time is clear, right? How much time it takes for the influence to go from the generator to the source. Clear? Okay. So transit time is basically defined as the time taken for the electromagnetic wave to propagate from the generator to the source. Okay. So it is basically the length of your transmission line divided by the velocity of propagation. So the length is given by 100 meters here and the velocity is 10 power 8 meters per second. Okay, so that is why the transit time is 100 by 10 power 8, which is 1 microsecond. Okay. So those quantities will come in the next question. So in the next question we have, what is the load voltage at t equal to infinity? So when we calculate the load voltage at t equal to infinity, then we need the other quantities. So you know this formula that the voltage at a time going to infinity is given by ZL divided by ZL plus ZG into VG, right? Where VG is the generator voltage, ZL is the load voltage, and ZL is the load resistance, and ZG is the generator resistance. Okay. So in our question, Zg is given by what? Generator resistance is 100 ohm and load resistance is 200 ohm. This is ZL, and the generator voltage is 12. So if you put in these quantities here, then you find that the load voltage at infinite time is equal to 8 volts. So this is the value at which the load voltage finally saturates at large times. Okay. So is this clear? Okay. Okay. All right. So then moving on to the next question, that is question 6. we have this lumped circuit diagram over here, where this is the source term. So this is my voltage generator. The voltage at the generator is equal to 12 volt, and the generator resistance is Zg, which is equal to 100 ohm. Okay, and Z0 is given, is the characteristic impedance of my circuit. ZL is the load resistance over here, and this is the length of my load of the transmission line basically. So Z equal to 0 represents the generator side, and Z equal to L represents the load side, and 100 meters is the length of the transmission line, and the velocity of propagation of the wave is 10 power 8 meters per second. So these quantities are clear, right? Because understanding the diagram is important in these questions. Okay. So now the question is, if I close the switch at t equal to 0, then what is the value of the load voltage at t equal to 4 microseconds? So physically, you can visualize this thing as the voltage travels, the current travels from the generator to the source. Okay. So the influence goes from the generator to the load via the transmission line. It, because the characteristic impedance and the load impedance are not matched, there will be reflections of the voltage, right? So in one transit time the voltage will travel to the load, then it will get reflected back to the generator in another transit time, then in the next then again in the next transit time there will be some reflection here because Zg and Z0 are not matched. So again this reflected voltage will go back to the load like this, again there will be reflection, and so on. Okay, and the time period of this reflection is of the order is equal to the transit time of the voltage. Okay, this is clear what I said? Okay, so what happens is that, okay, so when I close my switch, then there is a wave which propagates from the generator to the source, right? Generator to load. Okay, now the load impedance is not matched with the characteristic impedance of my circuit because ZL and Z0 are different, right? So yeah, so there will be a reflection of the voltage over here, and this reflected voltage will travel back along this line to the generator. Okay, this reflected electromagnetic wave, it will travel back along the line to the generator. Now you see the generator resistance is also not equal to the source characteristic impedance, right? So there will be another reflection over here, and another reflected EM wave will propagate from the generator back to the load. Again there will be another reflection from here back to here. So there will be a constant reflection between these two components. Okay, so in that way the load voltage at the load will keep on changing with the progress of time. So in order to find that at what time what will be my load voltage, I need to first calculate the two reflection coefficients. So the reflection coefficient at the generator, this is given by gamma g, which is Zg minus Z0 by Zg plus Z0, which is equal to 1 by 3. Okay, and the load reflection coefficient, that is the reflection coefficient at the load, is given by gamma L, which is ZL minus Z0 by ZL plus Z0. So ZL and Z0 are these. So this is equal to 3 by 5. Alright. Now at t equal to 0, what is the voltage at the generator end of the load? That means what is the voltage at this point at t equal to 0? Now the voltage at this point, that is Z equal to 0, is basically V0, which is Z0 by Z0 plus Zg into Vg. Right? Because Z0 is the characteristic impedance of the circuit and Zg is the generator voltage, and they are in series with each other. So the voltage at the z equal to 0 end of the load, that is given by this formula. Okay. This is clear, right? Up to V0 is not clear. Okay. So V0 is okay, clear. Okay, up to V0 is clear. So this is the initial voltage at the generator end of the transmission line. Okay. Now, like I had previously, my transit time t is given by length by velocity. So this is equal to 1 microsecond. Okay. So what happens in one transit time is that the EM wave propagates from the generator to the load. So at the end of one transit time, that is at the end of t equal to 1 microsecond, V0 reflects off at the z equal to L end of the load. So basically what I was talking earlier. So this initial voltage, it reflects off the load at the end of one transit time. Now at the end of the next transit time, there is another reflection which occurs. Okay. So voltage at the load is given by 4 plus 4 into gamma L. Right? Sorry, what? Huh? So after that, what happens is that in one transit time, there are multiple reflections at the load. Okay. Like I was saying earlier, that the EM wave traveling from here gets reflected here. Again, there is a second reflection which occurs here. And like this, there are many reflections which take place at the load, and all these reflections occur at intervals of one transit time. This is clear, right? What I said now? Okay. So at the end of first transit time, there is no reflection. So voltage is equal to V0 equal to 4 volts. At the end of the next transit time, there is a reflection which has occurred. Right? So that is why there will be an added voltage over V0. So this was my V0, and there is an extra voltage which comes in because of the reflection. No, 4 plus 4 into gamma L, where gamma L is the load reflection coefficient. Okay. Hello. Yes. Yes, yes. So there is a reflection at the load. So that is why the voltage at the load changes step by step. Okay. So yeah, that is why this at the end of 2 microsecond, the voltage changes by this amount. So the net voltage at the end of 2 microsecond is given by 6.4 volts. Then at the end of 3 microsecond, one more transit time passes. So there is another reflection, and the voltage changes by this much amount. So the net voltage is 6.4, which I got earlier, plus gamma L into 6.4, which is equal to 7 by 2 volts. Okay. Similarly, at the end of the next transit time, which is at 4 microseconds, there is another change in the voltage, and it turns out to be equal to 7.68 volts. So this relation is clear, right? How this voltage keeps on changing with multiple reflections at the load. Okay, okay. So basically it follows a simple relation like this, that the voltage, if Tn represents like the end of one transit time and Tn plus 1 is the next transit time, so then the voltage at the load at Tn plus 1 is equal to voltage at Tn into 1 plus gamma L. So you can write it like a generalized reflection, I mean expression like this. And then as you go further and further, if you go to t equal to infinity, that is at very large times, you will finally find that the voltage saturates to this value, which is the load voltage at t equal to infinity. So it finally saturates at 8 volts. Okay. Okay. So the next part is about current reflection, I think. Yes. So what is the value of the generator current at t equal to 3 microsecond in milliamperes? Okay. So the current reflection coefficients are basic. We have to, like previously we had the voltage reflection coefficients. Similarly, the negative of those quantities are the current reflection coefficients. So then the current reflection coefficient at the generator is minus 1 by 3, which is minus gamma g, and that at the load, and the current reflection coefficient at the load is minus gamma L, which is equal to minus 3 by 5. Okay. Now at t equal to 0, the initial current which starts off from the generator is given by V0 by Z0. Right, because V0 was my initial voltage and Z0 is the characteristic impedance of my circuit. So the initial current is equal to 80 milliamperes. Alright. So like we had at the end of one transit time, V was equal to V0. So at the end of one transit time, the generator current Ig is basically equal to I0, which is 80 milliamperes. Till this much is clear, right? Okay. So now what happens at the next transit time? At the next transit time, the wave reflects off the load. So what happens is that the current in the circuit in the direction of the load, it decreases, which means that there is a backward current going from the load to the generator. Okay, which is why I have this negative reflection coefficient for the current. So at t equal to 2 microseconds, the generator current is 80 plus gamma L into 80, where gamma L is equal to minus 3 by 5. Okay. So at t equal to 2 microsecond, current becomes equal to 32 milliamperes. This part is clear how it becomes 32, because it reflects off the load. Okay. So now after reflecting off the load, it comes back to the generator and then again reflects off the generator at t equal to 3 microseconds. Okay. So that is why it becomes 32 minus gamma g into 32. Now gamma g already has a minus sign, so minus minus makes it plus, and then Ig becomes equal to 48 milliamperes at t equal to 3 microseconds. Okay, so basically you will see that because of successive reflections, the current oscillates, and the oscillations, they gradually saturate to some value, which is the value of the steady state current on the load side. So that is our next question. So steady state current on the load side, that is current at t equal to infinity, is given by this formula, that is the generator voltage divided by Zg plus ZL, which is equal to 40 milliamperes. So finally, the current initially starts from 80 milliamperes, then because of successive reflections, it oscillates with damped amplitudes and then finally saturates to 40 milliamperes. Is this clear? Okay. Yeah, I mean, these problems. Yes, these problems are difficult to follow, but yeah, you have to keep a track of it. Like for me also, I had not done these things in my BSc or MSc ever. So even while doing the assignment, I had to learn the problems first. So yeah, this was slightly a bit different from what I know. Yeah, yeah. So do you want me to explain the problems once again? Which one? Mm-hmm. Oh, reflection at the load. Okay, okay. So, what is my transit time over here? Transit time is 1 microsecond. Okay, okay, okay. Now, transit time is basically the time period of successive reflections. So, reflections can occur at the end of every transit time. This part is clear because transit time is the time taken for the EM wave to go from the generator to the load, right? So that is why reflection can only occur at the end of every transit time. Okay, so that is why reflection is occurring at 1 microsecond, 2 microsecond, 3 microsecond, 4 microsecond, and so on, because these are all integer multiples of the transit time. Okay, that is why at the end of every transit time there is an added voltage, which is the reflected voltage, onto my load voltage, and this is how my load voltage gradually grows step by step and then finally saturates at 8 volts. Okay, no? Okay. Okay. Huh? Oh, saturation is a simple saturation you can obtain from this formula itself. Right, right. So that is why you can directly find out saturation, but how it goes towards saturation. So these are the transients. This is how it grows gradually with time before it saturates. Okay, okay. So these were all the questions I had. Are there any other things which you want to discuss? Yes. Plus one at equal to. Oh, okay, okay. So if as I suppose my Tn is equal to 2, then Tn plus 1 is this 3, right? Okay, so V at 3 is equal to V at 2 into 1 plus gamma L. So basically this is what I did over here. So at 2 my voltage was 6.4. So this is 6.4 into 1 plus gamma L. I get 7.2. Then next step, I do 7.2 into 1 plus gamma L. So this gives me the voltage at the next time. So this is like a general formula. So given any time Tn, how can you find the voltage at time Tn plus 1, which is the next transit time? Okay. Any other questions? Okay. Yeah, I have up to 8 only in this problem set. So, no, no, up to 8 only. Because 9 and 10 were on Smith charts and I did not have a Smith chart with me. So, yeah, I could not do those. So, if there are no further questions, then we can close the meeting for today and we can meet again next week. All right. Thank you very much. Okay, thanks.